Interesting phenomena, namely the temperature echo in proteins. It's not really specific to proteins, but it can be applied to proteins as well. It has to do with a so-called coherent motion of the atoms in a protein. We will see, I'm going to define it in more precisely what by these echoes we mean, and we are going to discuss methods how to produce these echoes. You are going to do that tomorrow morning, is my understanding. Originally, it was planned for this afternoon, but since you have to learn so many things, I mean, to get used to it with VMD and MD and so forth, probably it will happen only sometime tomorrow. There are three ways of doing that, namely the so-called temperature quench echoes, the constant velocity reassignment echoes, and the velocity reassignment echoes. In fact, the first two are particular cases of a last one, but it's easier to understand the first one. I mean, the temperature quench echoes, first one, and then we go to the more subtle one, subtle examples. All right. What is this temperature echo is all about? We know that the temperature and velocities are related. The kinetic temperature is related to the mean kinetic energy, and therefore by changing the velocity, if you change the velocity of particles in your system, in your protein during simulation, of course you are going to change the temperature as well, provided that the velocities are assigned or reassigned in a random fashion or in a fashion which does not conform with the Maxwell distribution of velocities. So this is the formula we use to calculate the kinetic temperature, the average of this temperature during a simulation for a sufficiently long time. It will approximate the so-called thermodynamic or equilibrium temperature. So this echo phenomenon is related to the fact that in proteins, what makes the proteins and the in general biomolecules so complicated system is because they involved dynamics on a time scale ranging from femtoseconds to seconds. I mean, the vibration, you know that you are limited by the time step of 1 femtosecond, which is related to the frequency of fastest degrees of freedom, namely the vibrations of a hydrogen atoms, of protons in a protein. But also the most important and most relevant biologically motion in proteins are the one which are taking place on a millisecond, microsecond, millisecond, or even second time scale. These are the large conformational changes, and which cannot be really studied using molecular dynamics so far, at least. I mean, even the folding of a smallest protein, it will take at least milliseconds. So it's a very time-consuming process, and if you start with a time step of 1 femtosecond, it's very difficult I mean, it's impossible at this time to get there, regardless of computer power you have. All right, now the simplest approximation to describe such a system, such a protein, is just to imagine that you have a bunch of harmonic oscillators, which are weakly interacting harmonic oscillators, which are also called normal modes. Now, a normal mode usually comprises the motion of vibrations of many atoms, so it's not an atom, a normal mode, but the motion of one atom is really a superposition of many more normal modes. So it doesn't come as a surprise that actually the vibrations of these normal modes are extending across the entire protein, or at least in different parts of a protein. So this is really a concerted motion of many atoms. And this is what makes coherent the motion of, or the dynamics of protein on a picosecond time scale. So this happens on a picosecond time scale. If you go to a longer time scale, all this coherence is lost. You can imagine, just like some of you may be familiar with the coherence phenomenon in physical optics, where you have two waves And if you make them to interfere, using, for example, the double-slit experiment, then you can get regions where the intensity is high and regions where the intensity is low. So by superimposing two finite quantities, you can get a vanishing one, 0, or you can get something which is amplified. This is a typical wave-type phenomena, resonance-type phenomena, which is related to interference. Now, you can expect that something like that can happen also in a protein if you assume that this harmonic approximation or almost harmonic approximation is a valid one. Because this phenomenon is expected to occur on a picosecond timescale, it means that it can be studied using molecular dynamic simulation. So let's see whether this can be done and how it can be done. So first of all, let's define what is this temperature equation about. Well, it's nothing but a sharp resonance-like feature in the time evolution of a protein's temperature. So you can monitor the time dependence of a temperature of a protein. You just use the output file or the log file from an MD simulation. And the system is equilibrated. What you will see, this is a simulation at 310K. You see that the temperature stays constant. So this is really a generic plot here of a temperature versus time. Let's forget about numbers. All what you have to know is that the time is of an order of picoseconds, and the temperature, it's about a few hundred K, say 300K, but you can do it at 200K and so forth. The smaller the temperature, the better is the approximation, because you know that the harmonic approximation holds better at lower temperature. As you go up in temperature, then anharmonic terms will kick in and will spoil the harmonicity of a system. Now, at a given time, say t equals 0, you send a so-called synchronizing signal. What is this synchronization signal? Is you set the velocity to certain values. For example, you can set them being equal to 0. Well, here it is not 0, but you are reducing dramatically the velocities of the particles. And you save that value, so you save the phase, basically, of the oscillators. You are forcing all these oscillators by setting the velocity at a given time to oscillate in phase. Immediately, the system recovers. This is not a surprise, because we discussed that we saw that the velocity autocorrelation function is less than 0.1 picosecond. Actually, here we will see that this temperature autocorrelation time, which is related to the square of a velocity, should be even smaller, and it turns out to be indeed of the order of femtosecond. So immediately the system recovers to its equilibrium temperature, and it starts fluctuating with respect to this value. Now, why does this happen? By changing the velocity, what you're doing, so reducing the velocity, you are removing energy from the system, and you are removing it from the kinetic energy. But of course, you have built up energy in potential energy, and that is not according to a Maxwell-Boltzmann distribution. So the system immediately, because it was perturbed, it wants to get back into equilibrium position. This is an example of non-equilibrium process. You're driving the system out of equilibrium. And even worse, you cannot really use linear response theory in a sense, strictly speaking, because the perturbation is in fact large, so that you are actually perturbing the system sufficiently strong to move it out. Nevertheless, because the system recovers so fast initially, and then slowly converges even more, reducing its fluctuation, you can consider that even if the very first stage of this cooling process, it is a strongly non-equilibrium one, immediately after that you can consider that the system is sufficiently close to equilibrium, and you may hope that linear response would work in this region, as long as you can figure out what is the actual perturbation, or how to treat this temperature quenching perturbation properly. Now, the system, as I said, recovers, and this oscillator starts oscillating again after they were forced to move in or to oscillate in phase. After a time, tau, delay time, which is up to you. It's up to the experimentalist or the computational scientist's discretion. It sends a so-called probing signal. So you are resetting the velocities once again. But you are not resetting the velocities randomly. You are resetting the velocities at time t2 in a way which is correlated to the velocities at time t1. The easiest way is just multiply each velocity with one and the same constant, for example. This is a very general case. And then what will happen if you're actually reducing the velocities again, the system temperature drops again, and then it recovers, and it will stay, it will fluctuate slightly about its average position, except for one or two, in this case, two particular times, tau 1 and the tau 2, where you see sudden dips, sharp deep features in the time dependence of a temperature. And this is what the echo is all about, because you are recovering the same type of feature which you are imposed on a system, you are enforcing on a system through the synchronization and then through the probing signal at a later time. It's just like something which comes back. What is the origin of this temperature echo? So this is a very nice exercise. You are going to simulate this, but we would like to understand what this means. So as I said, as I already anticipated, the system we are considering it as a collection or an ensemble of oscillators which have different frequencies. So they have actually a whole range or a whole distribution of frequencies. At t equals 0, we just assign the velocities. So the vi is an index of the atom, each individual atom in the system. You are just multiplying with a constant with a constant lambda, overall constant lambda 1, a given velocity ui, which is distributed according to the Maxwell-Boltzmann distribution corresponding to the initial temperature. If lambda 1 is smaller than 1, of course, you are reducing the temperature, but you can also heat it. If lambda 2 is bigger than 1, then basically you are raising the temperature, and the temperature echo feature, in that case, it will be actually a peak. It will not be a dip. At a later time, t2, you do the same thing as you did here, but you may choose a different value for lambda 2. But important thing is the coherence way as you assign these velocities, or this correlated way as you assign the velocities. So you are just rescaling the velocity. Now, after a time, a given time, you will see, or a so-called echo time, you will obtain an echo in a temperature, like a sharp feature, a deep-like feature, as I showed you before. And you can characterize, you can use this echo, namely the time delay, or the time of the echo when it occurs, and the depth of the echo, to characterize actually the coherence, the nature of a coherent motion in the protein. So we are actually, the questions which we are really would like to answer here is, what is the time scale on which this echo persists or appears in a protein? It is a measure of a coherence, of a degree of coherence of a system. So how long lasts this coherent motion of the atoms in a protein? We can consider at least three cases. One case is when lambda 1 and lambda 2 is 0. We are really quenching the temperature. We are reducing the temperature of a system to 0, both at t equals 0 and at t equal tau, the delay time. We can use a constant velocity reassignment where lambda 1 is equal to lambda 2, so we are assigning the same velocity u sub I to each, in both cases, to the atoms. So you do not change the temperature of a system effectively. Now the question is, will you get an echo then? Here is clear, you have a dip, another dip, and you would say, well, these echoes are just the resembles or the time delayed effect of these two temperature quenching. How about if the temperature now stays constant? You're reassigning the temperature, but you are not the velocities, but you are not really changing the temperature. Will such an echo feature occur? We'll see. Then the other case is when lambda 1 and lambda 2 are completely different. This is the so-called general velocity reassignment case, exactly the one I showed you. And we are not going to discuss more about this because it's really nothing really special compared to the previous ones, as in principle at least. So let me get you through again through the timeline of the event. First, you have an equilibrated system. You couple it to a heat bath at a given temperature. Everything is fine. You stop the simulation. You are done. This is the moment when you will start your hands-on session. You will be asked to run a simulation, to continue the simulation in exactly the same exactly the same startup files, namely the same velocity and coordinate output from this simulation. But in this case, you remove a heat bath. So you will consider a microcanonical ensemble simulation, an NVE ensemble. So it's just the protein itself. You have no coupling to any heat bath. Now, at time t equals 0, what you do, you do the first velocity assignment. You are going to quench the velocities. You are going to set all the velocities to 0. And then you let the system to relax. You have, again, no heat bath coupling. After a time tau, now the time tau, it will be different. Each of you will pick, or you will be assigned actually different tau values for the simulation, so that at the end we can combine all this data and then we can see how the depth of the echo depends on this delay time, which is a very important feature of the echo process, and which will actually determine the so-called dephasing time, which characterizes the time scale of coherent motion in proteins. You will get precise description of how to pick these values. There will be a website where you have to go. Each of you will get a tau value, and you will also have to provide then to feedback the result of your simulation, namely the depth of the echo, so that then we can combine the whole. So it will be a kind of concerted motion of yours too, or of your activity in this hands-on session, probably tomorrow. So the second velocity assignment occurs at tau equals 0. You are doing, for example, another quenching. You set it again 0, the velocities. And then you start monitoring the system. You are looking again to the relaxation of a system, no heat bath coupling again. So the simulation itself, it will be very simple. You do not have to write out any DCD files. All what you will need is just the temperature, which you can get it from the log file or output file in the MD simulation. Now, what can you expect? If you are doing this temperature quench echo, namely you are setting the velocities of all the atoms at time 0 and tau 0, you will find an echo at time 2 tau, precisely at 2 tau, not more, not less. You will see also a slight feature at 3 tau, but is really not a real echo. I mean, it will not be a pronounced echo. So the echo, it occurs only at 2 tau. If you use the constant velocity reassignment method, namely you assign the same velocity, u sub I, at time 0 and tau, you will find an echo at 3/2 tau. Interesting. And if you are using a general reassignment, so you are setting the velocity at t equals 0 to ui for atom I, and you multiply it by a constant lambda, which can be smaller than 1 or bigger than 1. Actually, lambda is nothing but square root of a final temperature divided by the initial temperature. It just simply comes from the definition of kinetic energy, relationship between the kinetic energy and the kinetic temperature. You will see actually 2 echoes, one at 3/2 tau and one at 2 tau. All right, so let's see how the simulation will go. You will get a pre-equilibrated system at tau 0 equal 300K. So again, I'm trying to lead you through the hands-on session which you will have on this topic. The simulation will be run on the NVE ensemble, as I said. You will get a configuration file. So in that configuration file, basically what you will have to change is only the time tau when you make the assignments, and that's all. So it will be very small modification which you will have to do. You will be given a PSF and PDB file for the starting binary coordinates and velocities, which are in a so-called common directory. This is, as you noticed in most hands-on, you will have a directory which contains all these important files which are needed in each stage of a hands-on session. Then you have a configuration file, equil.conf, which is located in this directory, 01. 01, it actually determines the first step of computer experiment, is this phase. It's the phase where you will have to continue to run a simulation in NVE, ensemble, or a microcanonical ensemble for a while, for about 500 femtosecond. It doesn't take long, it's maybe a minute or two. Then you have to extract the temperature. You have a script for that, which does it for you, and then you can plot the temperature. Now, once you plot the temperature, you can also go and calculate the different quantities, namely the average temperature, the mean square root value of a temperature, and also the temperature autocorrelation function. Now, the temperature autocorrelation function is very important. It's important because it tells you what is the time scale on which the relaxation of a temperature really occurs. And you see from a simulation, which I showed you, the results of a simulation, I showed you that this really happens very fast. So we really expect something of the order of femtosecond. So here is a real calculation here. So you have the fluctuation of a temperature, namely the instantaneous temperature minus its average value, for 500 femtoseconds. You calculate the autocorrelation function for this delta t, which is again is the deviation of a temperature from its average value or mean value. And you are going to fit it to this exponential curve. As we discussed, autocorrelation functions can be at the first, as a first order approximation, be approximated as an exponential. And here is what you get. Here are the experimental, the computed data in blue dots, and the red one is the relaxation curve. Again, we see an exponential relaxation at the beginning, and then it is followed by this fluctuating part, which is always, you will always get these tails, as we mentioned. We got it in the free diffusion case. You saw that yesterday as well for the Brownian oscillator. Here we get it again. But if you do the fit for the leading part, for the exponentially decaying part of autocorrelation function, you get that the relaxation time, it's about 2.2 femtoseconds. So it's a order of femtoseconds. So indeed, you recover you're going from the sudden, from the dramatic change of a temperature back to smaller fluctuation about the average temperature in a very short time. The average temperature turns out to be about 299 K, which is very good. I mean, we started with a pre-equilibrated system of 300 K, and the error, the root mean square temperature, is 6 Kelvin. So usually this is how you should give your results. I mean, without an error calculation, the results are not too meaningful. No numerical calculation is too meaningful. So the result is the temperature is 299 degrees plus minus 6. So this is your average. So it's definitely the 300 K falls into that range. Now, step 2. All the files you need, it will be in the directory 02 Quench A. It is Quench A because you are doing the quench for the first time. This is what you consider time t equals 0. Again, you will run the simulation for a given time tau, which will be assigned to you, as I mentioned before, through a web page. You will get the proper instructions at due time, and you have to assign the velocity. So you can use the set temperature to 0 feature in NemD in order to quench the velocities. Of course, an alternative is to use an input velocity coordinate file where all the coordinates are equal to 0. So that's another option to do that. But it's easier in this case, just set the temperature 0, which automatically means that all velocities must be set to 0. And then you do a second quench at time tau, and you let the simulation run. And this is what you will get. You will see that exactly at 2 tau, you have a sudden decrease in the temperature. You get a temperature quench echo. And here is the explanation of a phenomenon. So I'm going to go through this. I try to keep it as simple as possible. Assuming that we have harmonic oscillators, so you have a bunch of normal modes, which again is a superposition of a motion of many atoms. So you don't know what are exactly the coordinates x here. So this is not a coordinate of an atom, but it's really the coordinate which you associate to a collective, to a mode, a normal mode. It is just like a cosine function. The velocity, you just take the derivative. This is what it is. Now, this happens before before the first quench. At t equals 0, you quench the velocity. Namely, you set the velocity equal to 0. So at t equals 0, you set the velocity 0. If you set the velocity 0, it means that theta 1 must be 0 for all the atoms, or for all normal modes. So these are the expression for the normal modes at time after the first quench, but you impose the condition that V1 0 is 0. You can calculate what are the new amplitudes and what are the phases. Now, this is why you are talking about coherence. You are actually quenching the phase. You are fixing the phase. You force all these oscillators to be in phase. But the problem is that they oscillate at different frequencies, so they are going to dephase. Even if you forget about dissipation and anharmonic terms and so forth, those will just accelerate the extent of dephasing. At t equal tau, you do a second quench. After that, the law of motion and the velocity for these normal modes are given by this formula. I mean, very similar. Or what I did, I just changed the indices. I put 1 and 2 for the amplitude and for the initial phases. Now the initial phase, it will be again the same. It will not be 0, but it will be the same again for all the atoms, namely minus omega times tau. In fact, it will not be really the same for all the all the normal modes, because omegas are different. Nevertheless, they follow the same pattern, namely theta 2 is equal minus omega tau. And that turns out to be crucial. And why is that? Temperature is proportional to the mean value of a square of a velocity. You just take the previous expressions and express V2. V2 is the velocity after the second quench, and you get an expression which looks like this. Of course, you have to average here over all the frequencies and all the amplitudes, but that's not so relevant. What is relevant is that, for example, the average over the amplitude, it can be done, for the average over the initial phase, it can be done, and initial phase and amplitude can be done using the equipartition theorem, so that comes out. But what I'm really focusing on are the time-dependent terms. So actually this term here, I don't really care about these terms which are time-independent, because you're going to make an average and you get something which is proportional to the temperature, and that's it, or a temperature times a numerical factor. And this is exactly what you get. Namely, the temperature will be T0 divided by 2 times this expression, which contains 5 different terms, 1, 2, 3, 4, 5. 4 of those, I mean, this term is temperature independent. As I said, I'm not really care about this. This will actually average to 0, because I have to do an average over all the omegas, all the frequencies. And in general, we know that if you have cosine omega times any time-dependent function here, and you do an average with respect to omega, you will get 0, because the cosine is a highly oscillating function. The only way you get a finite value is then this question mark here is 0, and when you get that value, you get 1. And now let's go through this. This quantity would vanish only for t equal tau, but this formula is valid only for t bigger than tau, because at tau I quench the system. This quantity is just simply 0. because t cannot become ever 0, because I'm in the regime when t is bigger than tau. So the only interesting quantity is the last one. And the last one, as you can see, it will be 0 or almost 0 always except for t equal to tau, because exactly at t equal to tau, this is precisely 0 for all possible omegas, for all frequencies. So this is why it's a kind of resonance effect. So again, the idea is I didn't put here indices because I didn't want to put too many indices and to make this equation even more complicated than they look like. All the average here, these brackets here, really means average with respect to all the frequencies. So if you have different frequencies here and this factor is non-zero, then you get something which is vanishingly small. And actually the temperature will be simply T0 over 4. You reduce to 0 twice the temperature, which just simply means that after each zeroing of a velocities, the temperature, the average temperature will be halved. So you halved it once and you halved it another one. So after the second quench, you should expect a mean temperature of T04, except at t equal to tau. Because at t equal to tau, this is a 1, and you have to subtract from 1 minus 1/2. So you get another halving. So it means that this is actually the expression of your temperature, which exactly for t equal to tau, it will be T0 divided by 8. Otherwise, it will be T0 divided by 4. And this is exactly what you get if you do the simulation. You go down, this is the half of a temperature, of the initial temperature. After the second quenching, you reduce it by another factor of 2. And then you get here at 2 tau the echo, which has a depth of 1/8 of the initial temperature. And this is highly reproducible. Now, you can get a better estimate. This was a back of the envelope calculation, just simply to explain it to you. I mean, with zeros and ones. But life is not 0 and 1, as you can see. I mean, you don't really have a kind of delta function here and perfect lines here. You have fluctuations. So you really would like to see also what is the shape of this echo. I mean, it really doesn't go to the value of 1/8 of T0 suddenly, precisely at 2 tau, but 1 or 2 time step before. So you really want to see the line shape form, the form of the line shape of that echo. And that can be done if you recognize that the average of a cosine 2 omega t with respect to the all possible frequencies, normal mode frequencies, it is actually proportional. It is, in fact, equal to the temperature autocorrelation function or normalized temperature autocorrelation function. Of course, this is dimensionless quantity, and this one also has to be the same. And if you do the calculation, you replace all the cosines with this expression, you can express actually your temperature, time dependence of your temperature, in terms of the autocorrelation function. But again, the autocorrelation function, we know that it has a very short lifetime of order of 2.2 femtosecond, basically 2 time steps, 3 time steps. It means that in a final expression, I can just simply keep the one term which gives us the echo, namely the one corresponding to the argument of absolute value t minus 2 tau. And if this is actually the data from a real simulation, the one similar to the one you are going to do. What is the tau value in this case? It's 200 femtosecond, right? So you expect to get it at 400 femtosecond, the echo. And if you use this formula with the temperature autocorrelation function, which we already calculated, with this relaxation time, you get this fit. We can actually zoom in into this region, into the echo region, and you get a fairly good match between the theoretical curve and the numerical data, at least in the echo part. Of course, here you have also fluctuation. Now, this one, if you want to catch these features, then of course you have to take the more precise form or more complete form of the autocorrelation function. You remember here we are using the theoretical fit to the autocorrelation function. but we have the temperature autocorrelation function calculated from a simulation, so you can actually check that. In fact, you can show that the fluctuation dissipation theorem, actually in a linear response, you can connect precisely the fluctuations in a temperature to the temperature autocorrelation function, which is non-trivial. So the fact that you can express temperature as in terms of a temperature autocorrelation function is not trivial, but it can be actually proven rigorously using methods of statistical physics. Dephasing time. The depth of the temperature echo depends on the delay time of a tau, which I mentioned to you. So if you calculate, these are the black dots or circles. These are actually the calculated values of the depth. This is the depth of echo, as is shown here, as a function of a delay time for different values. So this is exactly what you are going to do. So you are going to calculate one of these points here, each of you. And once you are done with this, we are going to fit this to an exponential curve. And the time constant of this exponential factor will give us the so-called dephase time, which turns out to be about 854 femtoseconds, so it's 0.8 femtosecond, which is of order of picoseconds. So coherence is retained in proteins on a time scale of 1 picosecond. If you do it for a longer time, you won't see. So if you wait, the dephase time, it will be much longer than that. So basically here you are at 2 picoseconds. So you will still get some echo, but the depth is really decreased exponentially. If you go to even longer time scale, you will get actually nothing. The signal will not be there. So again, this is another example where by choosing the right values, numerical values for a parameter, namely the delay time, you can actually probe, you can learn about the internal dynamics of a protein in that particular scale. This is what all experiments are about. There is no perfect experiment, no perfect experimental method which describes all the features or all the properties of a system. Doesn't matter whether it's condensed matter or biological or whatever it is. You always have to tune your experiment to the certain problem or the certain range of a quantity which you are interested in and you want to study. In a constant reassignment, velocity reassignment, you can also get echo. So the idea is the following. You are forcing the oscillators, so these normal modes, to oscillate in phase by assigning the same velocity, by assigning a set of velocities corresponding to the same temperature T0 at time t equals 0. After a time tau, you reassign the same velocities. Okay, so it's, I mean, in molecular dynamics, this is very simple. You just save the velocities. You have a set of velocities. You just generate using Maxwell, according to Maxwell distribution, you generate a set of velocities to all atoms for all three components, Vx, Vy, Vz, for all atoms at a given corresponding to temperature T0, and you assign those velocities to the atoms at t equals 0. You wait a time tau, you run the simulation, and then you do the same thing. As you can see, nothing really interesting happens here. You have this usual fluctuation, pretty small fluctuation indicating that the system is in equilibrium. Now, the question is, can you get echo in this case? The answer is yes. Interestingly, you will find a huge decrease of a temperature, like out of nothing, at the time 3 tau divided by 2. And if you do an analysis similar to the one which we discussed before, you see that exactly at 3 tau over 2, you will have that cosine term there, which vanishes, or the temperature correlation function, whose argument vanishes, and the quantity becomes finite, which is subtracted from the mean velocity. And that's why you are getting this exponential light-shaped peak here. And now, of course, this is the expression for the temperature with which you can actually fit this. But I haven't shown here the fit, but you can actually try, and you will see that it works nicely. And now I have a question for you. Is it possible to produce temperature echo with a single velocity reassignment? So far it seems to be crucial that you send a synchronization signal and then a probing signal. But now the question is, can you imagine a case where you are running a simulation, right, and you have this problem. You may reassign velocities at one time. Can you obtain, without faking results, a nice echo?
Actually, don't tell them. Let them find out.
Maybe some there are answers, and maybe they, yes?
I mean, this is my guess. Probably we can save the velocities at one point and then assign the same velocity.
Sure.
We'll only have the theoretical echo.
Sure. Absolutely. So that is the answer. The answer is yes. And that is it. Reset the velocity. I mean, you just save it and then... Now, why don't experimentalists do this? Because an experimentalist usually... I mean, this can be probed actually experimentally. Because they don't know. They are not gods. They cannot go and look the velocities. They need a synchronization signal. They do it. They send a signal and then they probe it. This is how it happens. Even in some of you who know about nuclear magnetic resonance, the echo phenomena comes from there. Actually, there was observed for the first time. You always needed a synchronization signal and then a probing signal. But you know, in molecular dynamics, we can save velocities at a given time, and then we just reassign them. And this is what you get. Okay, very good. And I'm done. So we have a coffee break or questions, of course, if you want to.
Fewer questions.
And longer coffee break.
And then when we have, let's say, a 10-minute break, I just would like to tell you that we have the menu tutorial now available outside.
Yes?
Okay, I've got a brief question.
And then I go back to you. Okay. Yeah.
Sorry. I apologize. We have an important announcement with regard to these menu tutorials. As you can guess, we work really hard to get them completed, and now we tested it all for nights. People tested, and naturally some errors arose, and now Tim will make some announcements.
So there are, in doing these tutorials in the labs in the afternoon and the night, we will make 4 revision copies available in each lab for you. So as you're going through them, and this holds for all the tutorials this week. As you're going through them, if you come up with any conceptual errors that you see, anything that's not clear, the section could be rearranged to make it conceptually better for the reader. Please write that in these copies that'll be at the front of the computer labs. Okay, and they'll be provided for every tutorial, like I said. Now the NAMD tutorial in particular is kind of a beast. So, and we did find some errors, and we'll be providing a list of errata for the NAMD tutorial in particular.
Where will they be provided?
That will be provided in the afternoon session today.
So they will be provided in a sheet of paper for everybody?
Yes.
Okay. And now we also will put these revision tutorials here on the podium tomorrow morning. So you can also quickly write some notes there. It would be nice if you come a few minutes earlier to do this. Workshop like this really quite incredible on the board. And if you would help us by adding suggestions, that would be really wonderful. You can also make general commands, just write them somewhere. No, there's no back pages, double-sided. Write them somewhere on the margin, some general remarks. Every improvement is very welcome. Okay, so now we have the question. I apologize.
Yes, no problem. Yes.
I guess basically this relates to the slide where you show, I don't remember specifically what it was, but you showed the effects of having a different value of tau. Could you go back to that slide, please?
So for different values of tau. Okay. This one?
Yeah, so, I guess basically what I was wondering is that sort of a function
All right, so this is done in vacuum. You are simulating only the protein, so you don't have water. Now, once you put water in, I mean, in fact, you can do this experiment with water as well, but there you have to be careful because calculating the temperature, what the output you get from the NAMD log file is for the entire system. So you will have to make sure that you are just calculating the kinetic temperature of a protein itself. You will see the echo, but the echo will be reduced. So all what I can tell you is that this is just a simple explanation. Again, it's a minimal model. It's a minimal physical model to understand why it happens. It is remarkable. It's remarkable because you would be tempted to say that if you have so many high frequencies, I mean, it's a wide range of frequencies of normal modes, you superpose them, on the average you should get 0 for a cosine or a sine. But here you don't get it because you have those terms with the t minus 2 tau or minus 3 over 2 tau and so forth. That feature will persist even if you include anharmonic terms and if you include other kind of dissipations and other kind of nonlinear effects. But the effect of the amplitude will be reduced significantly. It may happen probably, I don't know, if you consider some very weird dynamics, that the whole effect will go away. I mean, you need some, if you go in an overdamped regime, obviously you won't get it because you have to be in the underdamped regime. That's why you see it only on this scale, on a picosecond time scale. Other questions? Yes?
As a continuation to this question, in your previous talk you said that since you simulate more than the decorrelation time of the velocities, you don't expect different results if you extend your simulation. Should we actually try to simulate more than the dephasing time? Or like in a simulation, is it safe to just consider the decorrelation time or should we look at the dephasing time?
Well, what happens here, you see, my previous question was related to averages. When you do averages, then that is important. But in this case, you are following the time dependence of a temperature, which can be expressed in terms of a temperature autocorrelation function. But don't forget that the relaxation time for the temperature autocorrelation function is 2 femtoseconds. So I'm definitely beyond that. So you have several time scales entering here. So the dephasing time, what it means, it proves the coherence of the atom's motion, but which shows up in a sharp feature in the time dependence of a temperature. I mean, it's either there or it's not there. I'm not averaging anything there. But if I want to calculate that, I mean, I'm not averaging in a sense, I'm averaging over all the atoms. So again, the temperature is the average kinetic energy of all the particles, or all the atoms in the system. Whereas here, or when you calculate it in terms of a temperature autocorrelation function, then obviously you get the right answer there. You may worry that the average, the averaging process you used to calculate the temperature autocorrelation function may not be right. But it is because the relaxation time there is extremely short. So you are safe. I mean, this is fine. You can go further and simulate your system for a longer time with larger tau values, and you will see that your echo is going away. So as you can see, what is really written here is tau, is the delay time when you do the quenching.
Okay. Question is, you always say that in any autocorrelation function, decays and damage and oscillations. I'm not quite sure I remember the explanation for those oscillations.
Well, you can always say that those are kind of finite size effect, and you can just simply disregard them because they are small. Some of them can be artifacts because whenever you calculate an autocorrelation function, it's just like you're shifting your results, you're getting less and less precise values for larger times values. But the fluctuation, then they are real actually. These are like, I mean, these fluctuations are there in the system, so it's, they are real. So you should take them. I mean, the fact that it's an exponential is not, that's a good first order approximation. But actually time correlation, the autocorrelation function, it has a much more feature-rich structure. And those have to do with those oscillations, fluctuations, for example, of temperature close to the echo. So you remember when we did that, we just got for the line shape really at the center of the echo. But the satellites, those oscillations, we didn't get them. I mean, to get them, you can obtain those basically if you calculate properly the temperature autocorrelation function.
You mean the fluctuations are real?
Yes, they are real. They are not really artifact, at least for the first few, but those have to decay also. If you will see that actually starts increasing, then it's something fishy. Because that would be some unusual resonance effect or something. I mean, you expect that the correlation, decays. But because these systems, it's a superposition of lots of oscillators, you can expect some resonance, some interference type effect even in the autocorrelation function. If a system is damped, then probably you get less of those. But you can never discard completely the inertial term. Okay. Yes?
So if you were watching the simulation with D&D, did you actually see it echo?
Absolutely. I mean, those are real. What?
You don't see the echo with VMD. He said VMD.
Oh, VMD. I'm sorry. I thought. Okay. I'm sorry. I thought that you mean that you take with an MD plot. You mean whether you see some strange things going on in the structure? No. I mean, you have no discontinuities, no jumps in the positions. You cannot do that, but for the velocity, you can do that. I mean, you would see that if you would use VMD to animate the velocity DCD file, but that doesn't make. Actually, no. Wait a minute. You can do that. You have this exercise, hands-on.
But the answer is simply you do not see it visually. If you plot the kinetic energy using the plot routine of VMD, you can see it.
Yeah, but if it uses the DCD, the velocity DCD, then it sees even a kind like a condensation effect because all the velocities jump to zero. And instead of having that hedgehog type of plot you already discussed with a Maxwell distribution, you will see that immediately it goes down and then it starts to inflate. So, but what's the meaning of it? It's just a way of representing all the velocities of a system in a way.
But
yeah.
You should appreciate that if you see this velocity signal there, that it goes down, and you can say the total kinetic energy is the kinetic energy of the number of atoms in the protein, thousands. And now the echo goes down by about 30–40%. That means you're losing at that point suddenly the kinetic energy effectively of 400 atoms. So it's a real big effect, but you still don't see it visually. But actually, I just would like to add one more comment. There is a very lovely, we wrote a very lovely tutorial on the echo for a summer school in Denmark 2 years ago, and we will make that also available on the program. We add an extra PDF file, and so you have then immediately the link. It's not possible for you to read it. I think it's about 40 pages, but it has all the derivations, the explanations, and it's a very nice exercise in non-equilibrium statistical mechanics, following Chantaleka's work, and at a level that any biophysicist can understand definitely in this computer system. So now let's just go for 10 minutes. Oh, very nice. Very nice.
Well, I mean.
That we should also put in the book.
Yes, I mean, it's beautiful. Yeah.